Welcome to the lecture on sampling within the lecture series on computer graphics at KAUST. So on this lecture, we will be developing a framework for sampling, which is very often needed in computer graphics. Just think about the distribution ray tracing, which we have discussed, where we needed to generate a certain number of samples which will either go through our pixel or are on our surface or are the rays towards a light source, etc. So in order to generate these samples somehow in a controllable fashion, we need to understand how this sampling will behave. We will often perform sampling of objects which are not just, let's say, a rectangle on which the uniform sampling might be rather easy, but already if we have a disk and we want uniformly distributed samples on this disk, we need to perform this sampling in some careful way. So in order to develop the framework for sampling, we need to start with understanding what is, for example, a measure. A measure is a function that maps an object into a R plus, mathematically speaking. So it assigns the some geometry, in our case, a certain quantity. Like, for example, a line could have a length. That would be a measure. Or in 2 dimensions, we will have an say, infinite plane, and for subset of this plane, a certain rectangle within this plane, we will have an area as a measure. We need to also formulate what is a power set so that we understand the mathematical terminology for measures. Power set of, for example, the R2 will be a set of all subsets of R2. So all possible subsets of an infinite plane will be a power set of this R2 plane. And if we are measuring an area, we define a function of this power set onto where the power set is the domain and the R plus will be the range. For measure, we have to have also a zero measure. For example, we have we define the zero measure sets as the power set of all subsets where the value is zero. So this would be, for example, all the points on the R2 where the area will be zero. Or, for example, all the lines on R2 which have zero area will also be part of this power set. And there are certain conditions which a measure mu need to fulfill. It is that there are, for an empty set, the measure is zero, and that a union of 2 subsets is the sum, the measure of those is the sum of measures of these subsets minus the intersection of these subsets. In order to define measures, to compute them, we need integration. Integration gives us the way to compute the measures, as for example here we can see how we are computing an area of a subset, where to this area all elements on this area are summed up together in our integral in order to define the area. The area is the quantity as a number, as a value in R plus. And such a measure can be then, however, modified to another measure. For example, we can add a weighting factor which will be which will again be mapped to R plus, and this weighting factor can, for example, cause us a radially weighted measure, as for example here, where we have an weighting factor that with the increasing distance from the origin will be weighting more and more a particular point within the subset. Like, for example, within the subset 0, 1 squared. And how can we compute it? We can compute it as a double integral over the x and y coordinates or dimensions. And we can see here that the dA has been expressed as dx dy. So by just evaluating this integral, we can define our new measure and compute the measure for a given subset. Integrals are also very useful in performing computation of averages of a certain function over a certain region with respect to a certain measure. So average of a function is an integral of the function with respect to a certain measure and integral of that divided by integral of that measure itself. For example, we can calculate an average value of a function f, where the function f, x, y, is equal to x squared. And an average value of such a function over the area of between x equals 0 and 2 and y equals 0 and 2 is 4/3. So we can easily calculate an average value of a function over a certain domain range, a domain. And choosing the measure, the right measure, the good measure, is often the crucial aspect. Once we have that, then, for example, we can calculate various averages, such as an average length of a line through the rectangle 0, 1 squared. So what would be the average length of a line segment that goes through such a rectangle? This can be calculated with having an appropriate measure. We can see here that the average length will be computed as for all lines which go somehow through 0 and 1 square, their length is here, and then we have divided it by the integral of the measure itself. So let's have a look at this example. If we are measuring lines in 2 dimensions. So first we need to think of how can we design the measure. What could be a good measure? And for lines, we can define lines through this formula, for example, where the x is defining the y coordinate for a line through 2 additional parameters, m and b, where the b is the offset, or we could also call it the y-intercept, because if the x is 0, b is the value where the y-axis will be, where the y-axis is crossed. And the m value is actually the slope. So this is a slope. We can define a slope-intercept space, MB, through which we can define all the lines. However, such a space, MB space, as we know that the M is basically a tangent of phi, where the phi is the angle of our slope, and the tangent is having various values. It goes from 0 to infinity for defining the values between the for defining the various angles for phi. So the slope-intercept space will not be a good measure because for various reasons. And one way how to define it is that the equal size bundles of line will not have the same measure. So for example, if we look at this case, just for the intercept part, the B part, we can see that the distances between these lines will change based on their orientation. So here the distance is the intercept. There are certain distances between the lines, and these distances are larger if the lines have a different slopes. It's the same set of lines, they are just rotated, but the B will have a different value. So this is not a good measure, and we can cope with this measure by multiplying the intercept with the sine of the phi angle, and then this will be a correction term so that the dB will be equal irrespective of the rotation. So generally, the measure, if it's a good measure, it should be invariant with respect to change of a coordinate system. And for example, it should give the same values for a square if it's just a square 0, 1, or if it's rotated by 45 degrees. So whether it is such a square or such a square, we should have the same value of a measure. So the dBdm as a measure is not a good measure of lines, but it could be corrected. So as I said, the dB can be corrected with the sine term, actually with the cosine term of the phi, not sine, cosine, and the slope can be also corrected. So, for example, a good measure for derived from dBdm can be measure where the d mu is equal to this term, where we have a scaling by the m in the denominator by this whole term. And the dBdm is not the only characterization or measure which we can define over a set of lines in 2 dimensions. We can have different ones. So for example, we can imagine, so just a second, here we can see another measure where we have the dB is corrected with the term cosine phi, and then we are not using the m, but we are using the angle itself of the slope. So not the tangent, but the angle. And this could be a good measure, which is already corrected with this cosine phi correction term. We could have differently defined lines, such as, for example, the lines defined by the term ux plus yy plus 1 equals 0. This is basically an description of an uh, in the of a normal where the normal will have the values uv, and such a characterization of a line or parametrization of the lines um, can have a measure which is similar to the previous one, which we can see here. And that would be an appropriate measure, which is not changing with the changing the coordinate system. And then we can have, for example, an AB as a characterization of line, where the A is the x-intercept and B is the y-intercept. So if we have our line, this is the coordinate system, here is 0, 0, and the line looks like this, then this will be the value of A, and this will be the value of B. So that is the characterization of a line through this x and y intercept space. And the measure for such an space defining lines will be an appropriate one, will be this one. But the question is there a measure which doesn't need any correction, which is a sort of a natural measure for lines? And it turns out that there is one which is called the normal coordinates of a line, where we are defining the line as an angle theta here, which is an angle of the between the normal of the line with the x coordinate, so it's this or with the x-axis. This is the theta, and the p is the offset of the line. How far is the line from the point 0, 0? So this normal coordinates defined as the line with this implicit formula, and for that the measure, the appropriate measure, is the dp d theta. So here we would not need any correction term to improve the measure so that it becomes fair. Once we have such a measure of lines, then we can use it, for example, for computing the average length of a line. So if we have the measure, and then for each measure, within that measure, we have a particular line, and we calculate what is the length of that line when it intersects, for example, the rectangle 0, 0, 1, 1. And then we are summing up the values, and also we are dividing it then by the integral of the measure. So this is the way how we can use these measures for computing otherwise complex characterizations of averages of certain geometrical objects. We can also define measures on lines in 3 dimensions. And for example, we can do it by intersecting first an xy plane, where we will have the point characterizing as the line, and then an angle. So if we have a space, we have a point in the xy plane, and then a certain solid angle, which is then characterized by the theta and phi angles, which are the polar coordinates, which define as the direction. So for such a measure, we can define the d mu, which will be then the dx dy. So this will be the dA, the differential of an area, and then the differential of the solid angle, the omega, is here, where we have the sine theta, d theta, d phi. Or we can define our measure on the lines through uh, uh, intersection of a sphere. So imagine we have a line, and this line is intersecting as a sphere with the sphere with the center of 0, 0, and there is one point which is intersecting another point which is intersecting this sphere, and these points have certain coordinates in polar coordinates, which will be the theta 1 and phi 1 and theta 2 and phi 2. So these coordinates will then be useful for defining as the measure and the differential of that measure, which is then defined through sine theta 1 d theta 1 d phi 1 times sine theta 2 d theta 2 d phi 2. So with these measures, again, we can calculate, for example, all the lines in 3 dimensions, where what is the average length of a line, for example, within a cube 0, 0, 0, and 1, 1, 1. So we have now defined the measure. Next, for defining samples, we will need to spend some time on discussing the probability and continuous probability. So let's define a random variable x, which is characterized through a certain distribution with which likelihood a certain value of x occurs. And this is defined through the probability density function, where the higher the function is for a certain x, the higher the likelihood for that x value is to appear. So for example, for a dice with 6 sides, we will have equal likelihood by throwing with a fair dice whether there appears a number between 1 to 6. So the probability density function is a uniform density function, which is then constant. And for defining a certain probability of occurring a random variable within a certain range between a and b, let's say, we can compute it through an integral of this probability density function. So, for example, we can define a probability of a random variable. Let's talk about, again, this discrete case of a dice, rolling a dice, that there will be a value between 1 to 3, let's say, occurring will be 50%, and 4 to 6 will be also the probability 50%. So this is the range which we are talking about here, A to B. The probability density function is always positive or equal to 0. So it's definitely a non-negative function over its entire range. The probability density function, if we integrate it over the entire range minus infinity to infinity, should sum up to 1. So the overall density function is an integral of it is 1. Now, integrating the probability density function over a certain range, or from 0, for example, to a certain value, will be the cumulative density function, the CDF, or cumulative distribution function. So we will will be using both of these in the future, in the next slides, to our advantage. Now, let's define a so-called canonical random variable, which is its probability is 1 and it's uniform over the entire interval 0 and 1, which is open on the side of 1, and its probability is 0 elsewhere. So, and if we will perform so this is 0, 1, and this is 1. So the integral of this will be 1, as we can see. So this is a valid probability density function, and it is a random variable which is defined in a which will be a very useful one for picking a random number between 0 and 1 in a uniform way. So in an unbiased way. So therefore, we will be calling this a canonical random variable. And the probability that this canonical random variable comes from a certain interval AB, which is a subset of 0, 1, is simply B minus A. Because we are integrating here, and its probability is 1 defined over the entire range 0, 1. So, and if we are integrating, the integral will be then simply the difference between B and A. So, for example, a probability that our random variable will be picked from between, let's say, 0.2 and 0.6 will be, the probability will be 0.4, which is just the difference. So this will be great random variable if we want to find some random point within the range 0 and 1. So we will get a very unbiased pick if we need to pick something from this range. But we will not have such a nice function for other geometries, like for example for a hemisphere. But we can change, we can perform a certain function on this canonical random variable so that we have a fair random point picking also for these more complex geometries. The continuous probability can be used for calculating something which we call an expected value of a random variable. So this is an average value if we will have randomly choosing values from the according to the probability distribution of our random variable, then the expected value will come as an average of those picks, and we can calculate an expected value of a real function. So not only of the random variable, but of a real function of this random variable as an integral where we have the function value and the probability density function, product of these two as a part of the integral. So we are summing up the functional value and weighting it with its probability. We can also define an expected value of a random variable according to certain probability density function, and that is where our function value fx will be equal to x. With expected values, we can perform a sum of two random variables, and the expected value of those is the sum of the expected values of the individual random variables. And this holds also for the functions of these random variables, because they are defining as random variables themselves. And these equations hold both in cases when our random variables x and y are correlated or they are independent from each other. In computer graphics, we can use the random variables which are then defined over various surfaces, various geometries. Like, for example, often we will deal with the hemispherical surface for the illumination problems. And there we will be defining a certain measure on this hemisphere, which should be fair, so that we can also randomly define samples from this hemisphere. In other cases, we will use the area as our measure and measure differential, and the area will be in 2 dimensions, dx dy, and when we will be dealing with the hemisphere, we will be our differential solid angle will be defined through the polar coordinates multiplied with the sine theta. The theta is the angle which is between the normal and the direction from a certain surface point, and the phi will be the azimuth of this vector around the normal vector. So let's say that our random variable alpha is a uniformly distributed random variable on a disk with a radius r. So if it's uniformly distributed, it can be on the disk anywhere with the same probability. So this probability is basically 1 over the area of this disk, and the area of this disk is PR squared, where the r is the radius of our disk. So if we are performing the integral of the entire disk, we will have the overall integral over the disk will be equal to 1, and for a certain subset, a smaller area, our integral will be something between 0 and 1. So we should define for our for the calculation of a smaller area, so within our disk, if we have our uniformly distributed random variable, we can be interested what is the probability that our random variable will appear in within the smaller disk, which has the radius r half. So what is the probability there? If it's a random variable, then we can perform the integral with the r smaller than r half, and we are multiplying the probability density function, which we have defined, with the surface area differential with the mu measure for polar coordinates. And once we calculate this, we will find out that the value here will be then r squared. So what is the integral of this? First, we are integrating over r, so that will be the r squared divided by 2 times p r squared, and the phi will be then this will be the result of our integration, and our values will be from r half to 0, so that will be r half is r squared divided by 4 here, which means that we can get rid of r squared from our fraction, and we will end up with phi divided by 8 pi, and phi goes from 2 pi to 0. So this will mean then if the phi is equal to 2 pi, then we can get rid of the pi and 2/8, so the value will be 1/4. So the probability that our random variable on the disk will be picked from the smaller disk with the radius r½ is equal to 25%, 0.25, or 1/4. So this is furthermore, we can define the expected value of a function which is defined on a 0, 1 square, 0, 0, 1, 1 square. And if we have a probability density function for pi for x, y, then we can again perform the same calculation of what will be the expected value on this square, meaning that what will be the value of the function, which is in this case x. So we are basically interested to know with this function. So we can see here, this is the probability density function times x. So the fxy is equal to x. And we are basically, based on this probability density function, interested what will be the average x coordinate. What will be the expected x coordinate if we pick a random random points within this 0, 1 square? What will be the coordinate x on average? And if we calculate again our double integrals here from 0 to 1 for x and y, we will come up with the value 2/3. So we can see that we can, with an expected value, we can find out what would be the random variable peak on average given a certain probability distribution. The expected value is tightly bound to the notion of variance, which you already are both familiar with from the probability and statistics. And the variance is the square of the difference of a random variable on average from the expected value. So what is the expected value of the square defined by a random variable and the expected value? It can be also expressed with this term, which says the means of the square of a random variable minus the expected value of the random variable squared. If the x and y are random variables and they are independent from each other, then the variance of these two random variables is equal to the sum of their individual variances. And we can use variance to calculate the standard deviation, which is which gives us an understanding of how much the expected absolute value is, how much the random variable is deviating from the expected value in absolute sense, so not signed. And it is defined as the square root of the variance. So we know this already And if we are expressing now the expected value and the means through samples, so we are sampling our our distribution, then with samples, if we are summing up the samples and dividing by the number of samples, we are reaching to the expected value. This is proportional to the expected value, and with a large number of samples, we are getting more and more confident that the expected value of the samples is actually the expected value of the distribution. And if n goes to infinity, then the probability that the expected value is equal to the average of the sum of the sample values is equal to 1. Now we have defined that the expected value of a function of a random variable is equal to an integral of the product of the probability density function and the function value of the random variable given a certain differential measure. And this is proportional to the average of the functional values for a particular set of samples. The higher the n, the more it is closer to this expected value. We can use this formulation now and slightly reformulate to give the basic formulation for the Monte Carlo integration. And the Monte Carlo integration is basically used for numerically solving an integral where we have a random variable following a certain probability distribution function. And we can see it here that now we have this product of fx px and the fx is appearing also here. And if we now represent the fx and px product as a gx, as a new function, then we can say that we can approximate the integral of the gx with the value of the gx divided by the probability density function. We often do not know the probability density function of a certain phenomenon, but we can approximate it with a certain probability density function. And the more this function is behaving similarly to the function g, the smaller will be the variance that, the higher will be the confidence that the expected value represented from the x random variable samples will be corresponding to the expected value and will be corresponding to the actual integral. The following conditions need to be fulfilled: that for all g values where the g function is not equal to 0, the probability has to be higher than 0. And probability has to be, density function, of course, has to be non-negative. So this is a way how we can calculate the integral of given a certain samples and a certain function with undergoing a certain probability distribution. Now, if we want to have a higher confidence that our sample set is representing our integral value very well, we will have to increase the n. And we have here the effect in Monte Carlo integration of a diminishing return. So the standard deviation is proportional to the reciprocal of square root of n. And the error in the estimate is behaving similarly, which means that if we want to halve the error, we have to quadruple the n. This is one way how to have a better precision, and the precision is increasing with the square of n. And the second way how we can increase the precision and reduce the variance is to use stratified sampling, meaning that we will be subdividing our domain into smaller domains. And if for each of these subdomains, we will be taking a representative sample for which we will be calculating then the value and perform the sum weighted by the reciprocal of the probability distribution at that for that random sample. Now we are coming to the topic of choosing random points and choosing it in a fair way. So, for example, if we have our canonical random variable, we can use it for sampling a one-dimensional interval between 0 and 1. If we have a square between 0, 0 and 1, 1, we can use for fair sampling not one canonical random variable, but two. And through this, we can generate sets of tuples of random samples or coordinates of these random samples. And this distribution will be uniform as well. So, if we would like to now turn these samples into the distribution for a disk, we could think of that we will simply turn our coordinates, our Cartesian coordinates, into polar coordinates, and then we will be having a fair random distribution. But this is not true. Our points will be much more distributed in the center and much less in the far further away they are from the center of our coordinate system. Therefore, we need to find a different way how to calculate the samples in order to sample such a domain as a disk in a uniform way. And there are two strategies which we can use for this purpose, and one is called the function inversion, and the second one is called rejection sampling. One is conceptually simple, and the second one is simple to implement. So for function inversion, now let's have a look at this CDF, cumulative distribution function, where we are calculating the probability between some x min and some value x. What is the probability that our random variable will have a value from this range? And now, once we calculate this cumulative distribution function, its inverse function will give us a good random samples if the input values will be the canonical random variables. So let's have a look at some probability density function px described through this formula. And if we will now integrate this probability density function into the cumulative distribution function capital Px, we will have this value, and we simply have to find an inverse function to this function so that we can find some fair samples on this which follow this probability density function. So here we can see, for example, that we have some fair samples, and they are generated from the canonical random variable, and the function here, which the canonical random variable is the input for, is the inverse of the cumulative distribution function. So let's come to the problem of sampling a disk in a uniform way. If we want to sample the disk in a uniform way, we can follow the function inversion strategy. And we know that for the disk, we will have the uniform distribution is equal to the reciprocal of area. So therefore, we can just perform the integration of this probability density function to get the cumulative distribution function, and with a dA, so differential measure of the area, which is equal to, in polar coordinates, r dr d phi. And if we are now integrating it, this will be the result of our integration. And now, if we have a two-dimensional domain and we can express the function as a product of two functions, each respective for or corresponding to one dimension, then we can perform the function inversion of these functions independently. And indeed, we can see that we can split this into a product of two functions, phi divided by 2 pi and r squared divided by capital R squared. And now we can simply just invert these functions to obtain the fair sampling of our disk. So our canonical random variable will be equal to phi divided by 2 pi, and from that we can devise that the phi will be equal to the 2 pi multiplied by the canonical random variable, and something similar can be defined for the r. So r squared divided by capital R squared is equal to another canonical random variable. And then if we want to find out what is then r, we just put the capital R on the other side and perform the square root of it. And we can see that this changes the our distribution of our random variable in a uniform way. So this concentric circles has been scaled up so that they correspond to the same area, and the same area will be then sampled with the same probability, so to say, and there will be not more samples closer to the origin, but they will be uniformly distributed. So this is how we can create fair sampling using the function inversion. For the case of a hemisphere, where the hemisphere is defined through the theta and phi angles, going from theta going from 0 to pi half, and phi as an azimuthal angle going from 0 to 2 pi, we can use again the same strategy given certain probability distribution, which is defined here, which has a certain cosine fall off. So the higher the value theta is, meaning the more far away theta is from the normal, so this is the theta angle, the higher the angle is, the cosine will be leading closer and closer to 0. So there will be an highest distribution on the top and less of a distribution of or probability on towards the, uh, the base of this hemisphere. N is here an exponent, which is the Phong exponent in this case. If we have this probability density function, we can again perform the cumulative distribution function through an integration, which we have performed here, and we are using the differential of the solid angle, which is this value here. And once we are calculating it for this probability density function, and we are performing we split the function into two, we will have for the cosine theta, this is how we will achieve the fair sampling of cosine theta, and for phi, this will be the formula for the fair sampling of phi. If we would like to get an actual vector or point on the surface in Cartesian coordinates, we will have the cosine phi, which is here, times sine theta, which is here. So if we have, and this is for n equals 1, meaning if we have a nicely diffuse surface, then this for n equals 1, the cosine theta equals 1 divided by 1 minus the canonical random variable and the square root. And as we know, cosine square theta plus sine square theta is equal to 1. So if the sine square theta is equal to 1 minus cosine square theta, and sine is then equal to this value. So, and our cosine square is equal to 1 minus the canonical random variable. 1 minus 1 is 0, and minus goes to plus. Therefore, here in the square root, we have the canonical random variable. And then for the sine phi, sine theta, we have here the product of these values. And for the cosine theta, we have this value as we have calculated it here for n equals to 1. So this way we can sample our hemisphere in a fair way given a certain probability distribution. Now let's talk about another strategy. Instead of a function inversion, how can we achieve a fair sampling? And this is called rejection sampling strategy. And the rejection sampling strategy will basically use a sample selection based on some known and simple distribution, and will reject certain samples which do not fit some more complex distribution. So, for example, and here we have our canonical random variable will be given by this function. So we have here a function code, and if we want to now sample certain disk, again, a unit disk, which goes between, which has a radius equal to 1. So it goes between 0, 0, and then minus 1, 0, and 1, 0, 0, 1, 0, minus 1 are the points on this disk. Then we can basically sample in a fair way the entire area of minus 1, minus 1, and 1, 1. And every time a sample comes outside of this disk, we reject it. So we only take samples which are then coming which are then inside this disk. And this is what this routine is doing. So we just pick one sample. So we have a loop here, and we are defining one coordinate of our random sample, x coordinate, between minus 1 plus 2 times r. So r function is the canonical random variable which gives us values from 0 to 1. And the same for y. And then if x squared plus y squared is smaller than 1, so meaning that it belongs to the disk, then we are done. Otherwise, we will be picking another random point. So this is called rejection sampling, because we are rejecting certain samples which do not follow our more complex geometry. We can do it for the two-dimensional case. We can do it also for example, rejection sampling, where we have a certain probability distribution. Let's say that our probability distribution, so our probability distribution function will look like this, and this will be the highest value. This will be the value n. So what we can do for our probability distribution between A and B, so let's call it this A and this is B, we can basically form some kind of a rectangle and perform a uniform sampling of this rectangle, and then pick only those samples which are under our curve defined by the probability density function Px. So, and we can see this here. So we are picking for x and a random coordinate for y random coordinate. So this goes between a to b x, and the y goes between 0 and m. And we are having here this canonical random variable obtained by the routine R. And then only if the y value will be smaller than probability at the probability distribution function evaluated at the x position, then we accept this sample. And if it's not smaller, then we reject it with our rejection sampling strategy. We can use rejection sampling also in 3 dimensions. For example, let's perform uniform sampling of a sphere, of a unit sphere. So what we can do is we can perform uniform sampling of a unit cube. Well, unit cube between -1, -1, -1, and 1, 1, 1 points. And we place a sphere just at the origin 0, 0, 0 with a radius r equals 1. And we would like to have samples, we would like to sample uniformly this entire sphere. So we can do it also with rejection sampling. So we sample uniformly our entire cube. And if the cube sample is not within the sphere, then we simply reject it. And the code for that is shown here, where we are picking the x coordinate, y coordinate, and z coordinate, and then we are evaluating whether the x, y, and z value is smaller than 1, which means that we are then within our sphere. And then if that's the case, then we have picked a random sample within this sphere. So this is how we can make a uniform distribution of samples within a sphere. But if we use the value of this length here, and we will be normalizing our x, y, and z coordinates to 1, we will move our samples on the surface of the sphere. And by this, we will be uniformly sampling not the sphere internal part, but actually we will perform a uniform sampling, a rejection sampling of the sphere's surface. So this is how we can perform a uniform sampling of a sphere's surface. Let's use several aspects which we have learned today on fair sampling, uniform sampling of a square defined between 0, 0 and 1, 1 as the random sampling of lines which go through this rectangle. And the choice should be uniform. Therefore, we will need to perform a certain definition of what is the probability of our what is the probability density function of our lines. Now let's define the lines by the normal parametrization, where we have our the normal parametrization is then d theta dr. That's the most natural parametrization, and we can see that it is defined as the by the angle theta between the x coordinate and the normal of our line, and the distance of our line from to the origin. So, and this measure which we define is then used for us to create a function of the probability density function. Now we can see that for various thetas, we will have various r's which go through this rectangle. So for example, if our theta is equal minus pi to pi half, so all the lines which will be basically having this angle with the normal, such a line, the maximal radius, which then we will still cross the 0, 0, 1, 1 square, will be 0. So only these lines will be going through this square when the radius is 0. And radius max is a maximal radius value where we still will cross through the square 0, 0, 1, 1. For some radii, this will no longer be the case. And for the first quadrant, which we define minus pi to minus pi half, it will be actually the maximal radius will be 0. Let's clean this up a little bit, and let's have a look at one more case. Actually, at the case where we already have drawn one line. So for the second case, we have theta is in the range between minus pi half to 0. So it is this quadrant. And minus pi half will correspond to a normal which has minus pi half with the x coordinate. So it will be these kind of lines. And What is the maximal radius with these kind of lines in this quadrant? Well, that would be again 0. And then for the 0, that will be these kind of lines. What will be the maximal radius? Well, it will be actually 1. So it goes between 0 and 1. And here we have already the answer. It is cosine pi. But let's come to this cosine pi. Just let's have this geometric relationship fully understood. If we look here, then we have here this trigonometric relationship. This is our hypotenuse, which is 1. And here we have our angle. And our angle is defined as r divided by 1 is cosine theta. So r is equal to cosine theta. That is defining it. So we can use the cosine theta here for defining the R max. Great. And for other quadrants, we will see similar relationships happening. We will not go into those details now. But now we have defined that for each quadrant, we have a function of R max based on the theta. And then we want, so we have the probabilities, if you like, given an entire range of angles within a quadrant, what could be the permissible range of R. And now we define a uniform probability distribution through normalizing this Rmax function with the integral of this Rmax function, which is, and we will not go to the details, which is equal to 4. So based on this, we can obtain the probability density function for uniform sampling of lines which go through this square 0, 0, 1, 1. Let's have a look at the cumulative distribution function from this probability distribution function. And that one looks not very surprising. This part will be 0, and then the cumulative distribution function is increasing, and at the end it is equal to 1, because 3 minus 1 divided by 4 is 3 plus 1 is 4, 4 divided by 4 is equal to 1. So we have here the cumulative distribution function. This is, by the way, the probability density function, which we have here, of the Rmax function. Now we have the cumulative distribution function, and that one we can invert. And once we invert it, we can get our uniform sampling. So we can see here that we have performed the inverse function inversion so that we can obtain our theta value, which is parametrized by the Xi values, which are the canonical random numbers, random variables, which are defined between 0 and 1. There are 3 regions in which we define the Xi, and always a different formula which defines then our theta. Once we have defined our theta, we can simply use another Xi canonical random variable in order to define one value between 0 and Rmax for that corresponding theta. And with that, we will have a uniform sampling of theta and R, and in this normal space, and we will be able to define this way our lines which pass through the 0011 square and follow the uniform distribution. So this was an example which was using the knowledge from this whole lecture for this practical example, which can be utilized in graphics for some particular tasks. Well, that will be all for today, and I thank you for your attention and see you at the next lecture.